Hello gems! Welcome to another video of ACE series. In this video, we are going to discuss previous year BITSAT questions from the chapter of Thermody or Thermodynamics. Okay, so if you're new to this channel, go check out the description box, know more about ACE series. And yes, I do videos without sponsors, so let's begin. So alright, we have question 1 and question 2 here on the board. So question 1 from 2009 says, a gas expands from volume V1 to V2. The amount of work done will be the highest if the process is isothermal, isobaric, adiabatic, or will the work done be equal in all the three cases. Okay, quite a simple one because work done is nothing but the area under PV curve, right? Work done for a certain process is nothing but the area under its PV curve. Okay, so we are going to draw the PV graph. Okay, first of all, so pressure versus volume, and plot the PV curve for each of this, and then just compare the area, right? Highest area means highest work done, because work done is nothing but area under PV curve, as I said. Okay, so volume expands from V1 to V2. Okay, now we'll plot it individually for each of these processes. So first one, isothermal, pressure is inversely proportional to volume. Okay, so the curve will be somewhat like this, right? Pressure inversely proportional to volume in an isothermal process. Okay, now for isobaric, pressure is constant throughout the process, right? Pressure is constant, so only the volume will change from V1 to V2. Pressure is constant throughout the process. Remember now that the area under each of this curve give their respective work, right? Respective work done. Okay, and now for adiabatic, we know that it will be also a curve like that, the isothermal one. Only difference is the fall will be more rapid. Okay, so for adiabatic one, similar like the isothermal one, but the fall is more rapid. Okay, now compare their areas. You will see that the isobaric one covers the maximum area under the curve. Okay, the isobaric curve covers the maximum area under the curve. Then comes the isothermal one, a little less area, and last comes the adiabatic ones, even lesser area. Okay, so the isobaric process covers, isobaric curve covers the maximum area under it, which means the work done in the isobaric process is maximum. Okay, so option B is the correct choice. That was a question from 2009. Now in question 2, you are supposed to find a relationship, I mean not that way, a relationship between the slope of isothermal and slope of adiabatic process. Okay, so actually this is a result, you should know it by heart. Okay, the answer that I am going to tell you, you are supposed to remember it. Okay, so the answer is slope of adiabatic process equals gamma times the slope of isothermal process. Okay, I'll just prove it. I'll leave you halfway. I'll give you the approach how it is supposed to be done. Now to find the slope, it is no difficult job. You are supposed to use PV equals constant for the isothermal process, and this is how we'll end up at the slope of isothermal process. Okay, so once we write this, we are going to differentiate this. Okay, so P into dV plus V into dP. Okay, applying the UV rule, U into derivative of V plus V into derivative of U. And now differentiation of constant is 0. So you can write P dV equals minus V dP, right? Now write dP by dV. dP by dV. This is nothing but the slope, if you see. Okay, change in y with respect to x. Okay, you can see that change in y with respect to x. This is nothing but the slope, and the answer that you will get over here, dP by dV, is minus P by V, right? Minus P by V. Okay, minus P by V. So this is how you find the slope of isothermal process. And for adiabatic process, you will follow the same approach. Only difference is you will write PV raised to gamma is constant. Okay, now differentiate this, find dP by dV. That will be the slope of adiabatic process. Okay, so the answer that you will get is minus gamma P by V. After solving this, the answer that you will get is minus gamma P by V. So you can easily see that slope of adiabatic process is gamma times slope of isothermal one, right? Slope of adiabatic is gamma times slope of isothermal one. Okay, so that is how you do question 2. Remember the answer as a result. Okay, slope of adiabatic process is gamma times the slope of isothermal one. Over to the next question. So question 3 over here from 2010 BITSAT. In this question you are given PV raised to gamma is constant. Now don't be in a hurry and read the question halfway and say PV raised to gamma is constant. The process is adiabatic. Wait, read the question properly. Okay, so PV raised to gamma is constant and it is given that gamma is unity, which means the value of gamma is 1. So this equation becomes PV is constant, right? So this process is isothermal and not adiabatic. Okay, the sole purpose of this question was to confuse you, okay, was to get you in hurry and make you mark that adiabatic option. PV raised to gamma is constant, of course, but gamma value is unity, which means gamma is 1. So PV is constant, okay, and that means it is an isothermal process. A moment of silence for those who fell for the trap in 2010. Okay, over to the next question. Question 4 over here, it is from the easy category. Previously I forgot to mention the question category. The previous 3 questions were from the super easy category. Okay, anyways, this thing is relative, right? What may be easy to me may not be easy to you. Okay, so you just focus on the question, not on the category. At the end of the day, it is me who is doing that racism. Okay, question racism. Okay, so in this question you have 1 mole of O2 gas. The initial volume of this gas is 22.4 liters. You are going to compress that gas isothermally such that its final volume is 11.2 liters. You can see that it is half of the initial value, right? This process is carried out at a temperature of 0 degrees Celsius. You are supposed to find the work done on the gas. First of all, work done on the gas, right? So what are these positive options doing over here? Work done on the system is negative, right? So option A and option B get out of the way. Okay, so the answer should be negative, and actually it is a very straightforward question because you'll directly know the formula for work done in an isothermal process, which is nRT log to the base E V2 by V1. Okay, so N is number of moles, which is 1. R value you can take it as 8.314. T, the temperature is 0 degrees Celsius. Place it in Kelvin. Okay, so plus 273, that will be 273 Kelvin, and log to the base E. You can see that V2 is the final volume by initial volume. Okay, final volume is half of the initial volume, right? Final volume is half of the initial volume. Okay, so V2 is V1 by 2. Okay, so V2 is V1 by 2 and V1 in the denominator. This V1 and that V1 will get cancelled and you'll be left with, okay, I can take that 2 on top and that will be, okay, I'll show you, 8.314 into 273 into ln. Okay, I'll write log E as ln, 2 raised to the power minus 1. Okay, I can write it this way. So I can get that ln, that minus 1 down, right, using the properties of logarithm. So this answer will be negative. As I said, once you solve this, the answer that you will get is option D. Okay, ln of 2 has basically a value of 0.693. Remember this. Okay, I don't know why this was not mentioned in the question. Anyways, remember that value now. Ln of 2 is 0.693. Once you solve this, the answer that you are going to get is this one. Okay, only solving is left. Let's go to the next question. Question 5 over here from 2014. In this question, a gas releases 20 joule of heat, 8 joule of work is done on the gas, right? And internal energy, the initial internal energy of the gas is 30 joules. You are supposed to find the final internal energy. So basically you can see all the terms of first law of thermodynamics over here, right? Heat, work, internal energy. So just apply the first law of thermodynamics, right? So it is a formula based question. So delta Q is equal to U plus delta W. Okay, so gas releases 20 joule of heat. So this value is 20, right? Minus 20. It is released, right? Heat released is negative, heat absorbed is positive. Okay, so this is by convention. This is one of the most fundamental thing that you learn in thermodynamics, right? So heat released is negative, so minus 20. Okay, now internal energy, change in internal energy, you can write it as U final minus U initial. Okay, I'll substitute 30 over here directly, no issues, right? U final minus U initial, which is 30 joules. Okay, plus this work done is 8 joules. Now work is done on the gas, it will be negative, right? Work done on the gas is negative. Work done by the system, see, work done on the system, negative. Work done by the system, there is profit, right? Work done by the system, positive, okay? Don't confuse it with chemistry, okay? So work done on the gas will be negative, so negative 8, okay? So minus 20, you final, minus here you'll get minus 38. So get it over here, 38 minus 20, that will be the final internal energy, which is nothing but 18, right? So 18 joules. Option C is the correct choice. Over to the next question. So question 6 over here, in this question you are supposed to find the value of delta P by P for an isothermal process. Okay, this was asked in 2012, a super easy question if you have paid attention to question 2, right? I guess question 2, yeah. Because there we discussed that slope of isothermal process is given by dP by dV, which is equal to minus P by V. Okay, dP by dV equals minus P by V. How did we reach over here? We use the relation PV equals K, right? PV is constant in an isothermal process, right? So then we differentiated this and we reached this relation. Okay, I'll just bring it in a better format so that you can see it over here. So dP by P, right, delta P by P, you can see that. So I'll get it in the differential format first, dP by P. Okay, dP by P equals minus dV by V, right? dP by P equals minus dV by V. So this is in the differential format. If you want to look at the bigger picture, you can convert this d small change into a bigger change, which is delta. Okay, replace that d with delta to represent a bigger change, a bigger picture. So delta P by P equals minus delta V by V. Okay, so the correct choice is option B. Okay, I hope the approach is very simple, right? So over to the next question now. So question 7 over here from 2010, it is from the refrigerator section of your thermodynamics. So I can call it as a cool question, okay? So in this question, it is given that the temperature inside the refrigerator in the chamber is minus 13 degrees Celsius. The beta, the coefficient of performance of fridge is 5. You are supposed to find the temperature of room, okay? Quite a simple question if you know the relation that beta equals T2 divided by T1 minus T2. Okay, you should also know what this T1 and T2 means. T2 will be the temperature of the sink. Sink in our case is the chamber, right? Sink in the case of refrigerator is the chamber itself, and T1 will be the temperature of the room. Okay, if you know this, you are good to go. You can just substitute the values and get the answer. If you don't know this, don't dislike the video. I have another formula for you. Beta is Q2 by W. Okay, by definition beta is Q2 by W, where Q2 is the amount of heat extracted from the chamber of that refrigerator. Okay, so Q2 is the heat extracted divided by the work done. Okay, so again you can write work as Q1 minus Q2. Now there is a direct relation between these two, heat and temperature, so you can replace this Q2 by T2, Q1 by T1. Okay, Q2 by T2, Q1 by T1, and again Q2 by T2. Okay, so that's how you can reach over there. Now let's just substitute and get the answer. So beta is 5, T2 is the temperature of the sink, right? Minus 13. No, place it in kelvins. Okay, so add 273. So that will give you 260, right? 260 divided by T1 is the temperature of the source or the temperature of the room minus temperature of the chamber, okay, which is again 260. So just solve this equation now. 5T1 minus 5 into 260 equals 260. Okay, so it will be 5T1 equals 6 into 260, right? 5 into 260 plus 260. This goes on the other side as positive. So 5 into 260, 5 into x plus x. 5x plus x is 6x. Okay, so T1 will be 6 by 5 into 260, that will be 5 5s are 25, 5 2s are 10, 52 into 6, that is 312 kelvins, right? 312 kelvins. I have to again convert it to degree Celsius now and see the matching option. Minus 273, that will give us 9 over here, yeah, 10 over here, so 39. Okay, so 39 is the correct choice. So like 320 degrees Celsius and 325 degrees Celsius, the room can't be so hot, right? Unless I'm there in. Over to the next question. So question 8 over here, it is from 2013. It is based on heat engine. Again, you can see that level has increased now. It is from the easy to moderate category now. Okay. So anyways, focus on the question. Source temperature is given as 427 degrees Celsius. Sink temperature is 27 degrees Celsius. You are supposed to find the heat consumed per second if the work rate, now this is work rate, okay, is 1 kilowatt. Okay, this is rate of work. You can say that. You can also see the unit, it is par. Okay, it corresponds to the unit of par. This is rate of doing work, which is nothing but par. Okay, it is not work, it is rate of doing work, which is par. Okay, so the thing that we are going to use here is one relation about the direct relation between the heat and the temperature, which is Q1 by Q2 equals T1 by T2, because everything is given in terms of temperature and we want it in form of heat. Okay, and then we'll use the work formula, which is Q1 minus Q2. I hope you are familiar with this term. T1 is the temperature of source, T2 temperature of sink, Q1 heat absorbed from the source, Q2 heat rejected to the sink. Okay, Q1 again heat absorbed from the source, Q2 heat rejected to the sink. Okay, now yeah, so let's find that out and then we are going to wisely manipulate this to reach our destination. Okay, so Q1 by Q2 will be T1 by T2, T1 by T2, but place this values in Kelvin, right? So plus 273, that will be 700 divided by this plus 273, that will be 300. So the ratio is 7 by 3, Q1 by Q2 is 7 by 3. Now I am going to wisely substitute for Q2 over here. Okay, I'm finding the value of Q2 in terms of Q1. Why? Because at the end of the day, I know I have to find heat consumed per second, right? Heat consumed is nothing but the heat which is absorbed from the source, right? That is the heat which is consumed. Okay, so I want to find Q1 per second. Okay, so I am not eliminating Q1, I am eliminating Q2. Okay, I am going to place the value of Q2 in terms of Q1. Okay, keeping Q1 intact. So Q2, so no more talks, let's do it. Q2 is 3 by 7, right? 3 by 7 of Q1. Okay, let's place the value over here. Q1 minus 3 Q1 by 7. So that will give you 4 Q1 by 7. Okay, now we want the heat consumed per second. Okay, so let's divide this by 1 second. Okay, so that's how we'll wisely manipulate it. So work, so I'll divide it by 1 second on both the sides. So work divided by 1 second, and here 4 by 7 Q1 divided by 1 second. So this is the thing, this thing in parenthesis is the thing that we want, right? Heat consumed per second, Q1 per second, right? So let's name it Q dash. The value of Q dash will be 4 by 7 into 1 kilowatt, right? This is nothing but rate of work, right? Rate of work is given as 1 kilowatts. Okay, so this value will be 1.75 kilojoules per second. Okay, now you are supposed to convert it in kilocalories. You can see the options are in kilocalories, so we have to divide it by 4.2, right? Because 1 calorie is 4.2 joules, right? So if you have that many kilojoules, or I can say 1 kilocalorie is this much amount of kilojoules. So if you have 1.75 kilojoules, it will be 1.75 divided by 4.2. Okay, I made a small error over here. This value is 7 by 4, right? 7 by 4. Okay, anyways, the answer that I wrote over here is correct. 1.75 kilojoules, and that you have to divide it by 1.75 divided by 4.2, and the answer that you will get is option A. Okay, because you want the answer in kilocalories per second. I hope this is clear. Let's move to the next question now. Question 9 over here from 2012, it asks us which of the following is possible according to first law of thermodynamics. This is how I used to write my school assignment. Okay, I used to write big A S S I G N, and then I used to realize there is no place for MENT, so I used to squeeze that in. Okay, anyways, lovely memories. Let's get back to the question. So there are actually two ways to do this question. One is the logical way, or second one we can use the formula way too. Okay, so let's go by the logical way first. Okay, so we'll consider this two to be true and we'll see if it implies the third one. Okay, so for instance, take option A. So it says that work is positive, heat is negative, will the internal energy be zero? Okay, that is how we are going to take it. So work is positive means work is done by the system, right? Profit. So work is done by the system, heat is released. Okay, heat is released by the system. Will the internal energy be negative? No, right? Because if you see work is done by the system, heat is also released by the system, which means from where did this came from? First of all, this came from internal energy itself, right? Work was done by the system, heat was released by the system. It came from the expense of internal energy, right? These two things came from the expense of internal energy. The system had to spend its internal energy in order to do some work and release heat, right? So the correct option should be, there should be a decrease in the internal energy, right? If work is done by the system and heat is released by the system, there should be a decrease in the internal energy, because it is doing the work and it is releasing the heat at the expense of internal energy. So hence there should be a decrease in the internal energy, and option C is the correct choice, right? Work done by the system, heat released by the system, there should be a decrease in the internal energy. Internal energy should be negative. Change in internal energy should be negative, right? So this was the logical way. We did it without touching the board. Okay, almost without touching the board. Now let's do it by the formula way. Okay, so we'll use the first law of thermodynamics. Delta Q is equal to delta U plus delta W. Okay, so let's watch it in the form of internal energy, since everything is given in the form of internal energy over here. So delta Q minus delta W. Okay, so take case 1 and we'll get our answer directly. So case 1 says work is positive, so minus sign of the formula, work is positive. Okay, fine. Heat is released, negative, right? So it is given that heat is negative. So what will be the change in internal energy? You can see that this is negative and this is negative into positive, negative. So the change in internal energy is negative, as I said. Okay, so option C is again the correct choice, right? Let's just see for option 4, although it won't be correct, but let's prove it wrong. Okay, because it has something different to say, right? Work is negative. It says work is negative, so negative sign of the formula, work is negative, and heat is positive. Okay, so will the internal energy be negative? No, you can see that internal energy, this will be negative into negative, positive. So positive plus positive will be obviously positive. So internal energy will be positive, which is not the case over here. Option D is incorrect. Okay, correct option is option C. Internal energy should decrease if work is positive and heat is negative. Over to the next question. So question 10 over here. In this question from 2015, a gas goes from state P1 V1 to P2 V2 by two different processes. Okay, so I hope you are able to visualize this. You are supposed to tell me a quantity that remains same in both the processes. Okay, so basically a state function. Okay, let's visualize that if you're not sure what's happening. So let's draw the PV graph over here. So suppose the state 1 is over here, P1 V1, it goes from state 1 to state 2, P2 V2. Now it has two different choices. Let one choice be this, right? One process takes it from P1 V1 to P2 V2. It can also go in some other process, right? It can do such a thing by two different processes. This is process 1, and choose any other random process, suppose this one. Okay, this is process 2. Okay, you are supposed to find a quantity which will remain same in both these processes. Okay, so you are supposed to find a quantity which is path independent, a state function. As I said, the quantity should only depend on the initial and the final point. And you can see that in both these processes, the initial and the final point is the same, right? From P1 V1 to P2 V2. Okay, so find a path independent property or quantity, sorry. Okay, so if you know, heat is not a path independent, it is path dependent, it is not a state function. Also work is not a state function, out of the option. Now the answer is given in hidden format. You have to apply the first law of thermodynamics for it. So let's write it: delta Q equals delta U plus delta W. Okay, if you know, this internal energy is a state function, right? It only depends on the initial and the final state. Okay, so here you can see that delta Q minus delta W is equal to delta U. So this is a state function, as I said. So it will only depend on the initial and the final value. So for both of these processes, since the initial and final value are same, internal energy will be the same, and internal energy is nothing but delta Q minus delta W. Option C is the correct choice. Okay, let's move to the next question now. So question 11 from 2006. In this question you have 3 moles of hydrogen gas, which is a diatomic gas. Thanks for telling me that. So which is kept in a container whose walls are insulated. You are going to compress that gas in such a way that its final volume becomes half of the initial volume. Okay, just compress it so that its final volume is half of the initial volume. By what amount does pressure increase? Okay, when you carry out this process, by what amount will the pressure increase? Now something is hidden over here. Okay, the hidden thing is that the walls of this container are insulated, which means that there will be no exchange of heat. Okay, this process is adiabatic. Okay, dq is 0. Walls are insulated, there will be no exchange of heat. This process is carried out under adiabatic condition, which means delta Q is 0. Okay, that is not relevant over here. What we are going to use is PV raised to gamma will be constant, right? For adiabatic process, PV raised to gamma is constant. So we'll use P initial into V initial raised to gamma equals P final into V final raised to gamma. Okay, so like terms together, P initial by P final equals V final by V initial raised to gamma. Now gamma for a diatomic gas, the value for gamma is 7 by 5. If you don't know it direct, you can use the relation of gamma with degree of freedom, which is 1 plus 2 by F. Okay, now you should know the degree of freedom value for the diatomic gas, which is 5. Okay, so that will give you 7 by 5. Okay, 5 plus 2 divided by 5, which is 7 by 5. Okay, as I said, the value for gamma is 7 by 5. So let's substitute everything over here now. V final is half of V initial, so this ratio will become half, right? V final by V initial will be half. So P initial by P final equals half raised to power 7 by 5. Gamma is 7 by 5. So you can see that P final, okay, P final is 2 into 2 to the power 7 by 5 into the initial volume. Okay, so you can see that pressure has increased 2 to the power 7 by 5 times the initial pressure. Okay, so this was the thing what you were asked for. By what amount does pressure increase, right? So final pressure is this much times the initial pressure. Okay, so it has increased by this amount, 2 to the power 7 by 5. Option A is the correct choice. Okay, so only this thing was hidden over here, that walls are insulated means the process is adiabatic and you have to use this approach. Okay, I hope that is clear. Let's move to the next question now. Question 12 over here, it is from BITSAT 2017. In this question, you are given a PV graph, and on that graph, you are shown 3 processes. Okay, one is ACB, one is AB, and one is ADB. Okay, you are supposed to compare their heats, find the relation between their heat, and then tick a option among this which is correct, right? Obviously. So one thing to note over here, one very important thing is that each of this process starts at state A and ends at state B. Right? If you see process 1, it starts at A and at B. Process 2, it also starts at A and at B. Process third also starts at A and ends at B. So basically you can see that their internal energy will be the same, right? Internal energy is a state function. It only depends on the initial state and the final state, right? Which is same in all these three processes. Hence, internal energy for all these three processes will be the same. So you know something about internal energy of these three processes. You are supposed to find what is the relation between their heat. So can we use first law of thermodynamics, right? So delta Q equals delta U plus delta W. We don't know about the work, right? But we can make interpretations about work from here. Now this you'll know, I guess. So in a PV graph, if the cycle is clockwise, okay, if the cycle is clockwise, work done is positive. Okay, work done will be positive if the cycle is clockwise, and if the cycle is anti-clockwise, okay, anti-clockwise, the work done will be negative. I hope you know that. If you didn't knew this, write it down somewhere. Okay, notes will be available in PDF format on the website too. Anyways, come back. So let's find the relation now. Now it's easy, right? Because let's write it for process 1 now. The heat in process 1 will be delta U. It is same for all the three processes, delta U plus what is the work done in first process. Okay, you can see that it will be something positive because the cycle is clockwise, right? The cycle is clockwise. Okay, so here the work done will be something positive. Okay, now in the second case, if you see, it will be internal energy plus the work done. In this case, if you see, it is perpendicular to the x-axis. Okay, it is perpendicular to the x-axis. You can see that basically there is no change in volume. Work is defined as P delta V, right? So if there is no change in the volume there, then there will be no work, right? Sorry, I'm fumbling a bit, but okay, so the work done in the second process is 0, and now let's find the heat in the third process since we want a relation between them, right? So internal energy same as the other two, okay, plus the work done. What will be the work done in this case? It is anti-clockwise. You can see that ADB, this third cycle is anti-clockwise. Work done will be something negative, right? So if you see, this Q1 is the highest value, right? Q1 is the highest value. It's internal energy plus something, right? Internal energy plus something. Then comes Q2, which is just internal energy, and then comes Q3, which is internal energy minus something, right? So Q1 is greater than Q2 is greater than Q3. Okay, now find a relation that fits in. Q2 greater than Q1, Q2 no. Here Q2 is the least, no. Q3 is the least, none of them are equal. Q3 is less than Q2. Q3 is less than Q2, right? Q3 is less than Q2. Option D is the correct choice. I hope the approach is clear. The only catch point was over here. Okay, let's move to the next question now. Question 13 over here. In this question from 2009, we are given a PT graph, okay, pressure versus temperature graph. You are supposed to guess or find the corresponding PV graph, okay. PV graphs are there in the option. You have to find a graph corresponding to this PT graph. Find a PV graph corresponding to this PT graph. This might seem a difficult job, but trust me, this is no difficult job, okay. And now that you have made so far in this video, I hope you trust me. Okay, and if you trust me, subscribe. Anyways, let's come back to the question. So we'll consider each process one by one. Let's consider this AC as one process, and if you see in AC, temperature is constant, right? In this process AC, temperature is constant. Temperature is not changing its value, which means it is an isothermal process, right? So process AC should be isothermal. Let's come to PV graphs now. Process, and we know that process AC should be isothermal. In isothermal, how do you represent isothermal curve on an PV graph? It should be falling down, right? Pressure inversely proportional to volume in an isothermal process. So here you can see, no, this won't be the correct one, right? AC is a straight line. You can see that going down. Here it can be the one, right? AC, right? It's falling down, pressure inversely proportional to volume. You can see it over here. Now here also AC is a straight line. That can't be the case, right? And even, okay, even here it is not the case. Option option B is the correct choice. Okay, AC is an isothermal process. You can look at the other processes too. Let's just verify that. CB, if you see over here, is isobaric, right? Pressure remains constant throughout CB, so it is isobaric. And here also, if you see, yeah, pressure remains constant throughout CB, which means it satisfies this too. Let's finally look for AB. AB, if you see, pressure and temperature are directly proportional, right? Pressure and temperature are directly proportional, which means if you apply PV equals nRT, and if I say pressure directly proportional to temperature, I mean volume is constant, right? Volume is constant. So here you can see that which one was that? AB, right? In AB, volume is constant. Pressure directly proportional to temperature, volume is constant. So this B graph satisfies all the three processes, right? AC, CB and AB. So this is the correct choice. Okay, I hope that was easy. Let's move to the next question. Question 14 over here. In this question, you are given a gamma value for a particular gas. It is 1.5. It is also given that the gas undergoes a certain process in which delta W, the work done, is equal to the internal energy. Okay. Now don't mistake this for adiabatic process. In adiabatic process, let's write the first law of thermodynamics. So in adiabatic process, you can see that this will be 0. And if you see, minus of internal energy is equal to the work done. So this is not adiabatic, okay? So you are supposed to find the molar heat capacity. So it is a typical one. Do it with me. So let's do it. So what we'll do is we'll write the first law of thermodynamics, delta Q equals delta U plus delta W. Now we know that both of these values are equal, so I can write it as 2 times delta U. Right, you can also write it as 2 times delta W, but if we write it as 2 times delta U, that will be easy because we know the formula for delta U, right? It will be NCV delta T. This is not the thing that we are asked for. We are asked for find molar heat capacity. This is molar heat capacity at constant volume, right? So the formula for delta U is this, NCV delta T. This is molar heat capacity at specific volume. Okay, now Q can be written as delta Q can be written as NC delta T. This is the thing that we are supposed to find. If you know, heat capacity is given as delta Q, the amount of heat that should be given per mole to change the temperature by 1 unit. Okay, this is the value for heat capacity. From there you can make heat a subject and you'll get NC delta T. Okay, NC delta T. This N will cancel with that number of moles, same on both the side. And now you can see that this delta T will also get cancelled. You'll see that C is 2 times CV. Okay, one more formula for CV. Do you know it? CV is FR by 2. Okay, FR by 2. CV value is FR by 2. F is degree of freedom. R is this constant. Okay, now how will we go about this? We know we don't know about the degree of freedom, right? So we can use the relation between gamma and F. Okay, gamma and F. Gamma is 1 plus 2 by F, right? So we can use this relation because we know what the value of gamma is. So we can write F in terms of gamma, right? So it will be gamma minus 1 equals 2 by F, which means F will be 2 upon gamma minus 1, right? Okay, so F will be 2 upon gamma minus 1. So let's substitute it over here. This is 2 into CV. CV is F by 2. F by 2 into R. This and this will get cancelled. FR. F in place of F, you can put 2 upon gamma minus 1 into R. Gamma value, you already know it as 1.5. So 2 divided by 1.5 minus 1. 2 divided by 0.5, which means 2 divided by half, which will be 4. Of course, there is R over here, right? Now 2 divided by half is 4, right? So 4R. Okay, so on this side we had C equals 4R. Okay, on the left hand side we had C. So C equals 4R, C equals 4R, A, option A is the correct choice. Over to the next question. I'll just explain you the approach. We applied the first law of thermodynamics first. Then we said these two are equal. We just replaced it by 2 times delta U. Delta U formula is NCV delta T irrespective of the process, right? And here delta Q, we wrote it in the terms of molar heat capacity, which is NC delta T. And then we found that this N, number of moles, get cancelled. The temperature difference also get cancelled. Okay, so C is 2 times of CV. C, this heat capacity, molar heat capacity, is 2 times of the molar capacity at the constant volume. Okay, and then we substituted the formula for the CV, which is FR by 2. 2 and 2 got cancelled. F, we wrote it in terms of gamma since we didn't knew its value, right? We didn't knew the nature of gas, its atomicity, we didn't knew that. So we wrote it in terms of gamma, which was 2 upon gamma minus 1 into R. We substituted the value, we got the answer. Okay, I hope the approach is clear. Over to the last question. Question 15 over here from 2018. This is your last question. Then I'll give you your homework question and then I'll take a leave. Okay. So in this question, you can see a nice Carnot cycle over here. AB is an isotherm at T1. DC is isotherm at T2. Okay. They are isothermal processes, AB and DC. BC and AD are two adiabatic processes. Okay, BC and AD. Okay, so that is a Carnot cycle happening over there. Volume of A is given, volume of B is given, volume at A, volume at B, volume at C, and you are supposed to find the volume at D. Now the approach is not very evident, right? How will you approach this question? Actually, I'll tell you the shortcut method first. So actually in a Carnot cycle, VA into VC, volume at A into volume at C, equals volume at B into volume at D. I'll write what I said. So VA into VC, VA into VC. So this is the shortcut way. I'll tell you how this came from where it came. So VA into VC, VB equals VB into VD. Why am I fumbling? Okay. Now you want to find VD, right? So VD will be VA into VC, VA into VC, which is 16, divided by VB, which is 8, right? So the straightforward answer is 4. 2 into 2, answer is 4. Okay. Now first of all, from where did this come? So we'll write the equations for each of these processes. Like for isothermal, we'll write PV is constant. For adiabatic processes, we'll write PV raised to gamma is constant. So let's write that. So PA VA equals PB VB, right? For the first isothermal process, I wrote that PA VA equals PB VB. And now I'll write for this adiabatic process PB VC PB VB raised to gamma equals PC VC raised to gamma. Okay, then I'll write again for this isothermal process now PC VC equals PD VD, isothermal, right? Now again write for this adiabatic one. Okay, now you can see the answer over there. So PD into VD raised to gamma equals PA into VA raised to gamma. Now if you multiply all these 4 equations, you will reach over here. You can see that PA, PB, PC, PD will get cancelled, right? They are there on both the side. Okay, so if you multiply all these 4 equations, you will be left with VA into VB raised to gamma into VC into VD raised to gamma equals VB VC raised to gamma into VD into VA raised to gamma. Now bring the like terms together. Let's bring VB and VB together. So VB raised to gamma minus 1, right? This will come in the denominator. VB raised to minus 1, VB raised to gamma minus 1. Okay, I just brought this VB over here. Similarly, let's do it for the other terms. I'll get VD over here similarly, right? VD, where is that VD? This should be VD, right? Yeah, Vd, let's get it over here. So Vd raised to gamma minus 1 equal to, now I'm lost again. So Va raised to gamma minus 1. Deep breath. Okay. And finally, Vb raised to, Vc raised to gamma minus 1. Okay, this Vc will go over here and it will make Vc raised to gamma minus 1. So you can say that on both the side, the terms are raised to gamma minus 1. So you can just remove that and you will get the result Vb into Vd. Vb into Vd equals Va into Vc. Okay, Vb into Vd equals Va into Vc. Am I fumbling? Okay, so Va into Vc equals Vb into Vd. Okay, so that was the shortcut that I told you. It came from this concept. Okay, I applied the equation for all the processes, isothermal as well as adiabatic, multiplied them, solved them, and hence I obtained this. Okay, actually if you see the derivation of your efficiency of heat engine, I guess, so there you will find this. There you'll find this in the derivation. Okay, so I'll recommend you to remember this as a result. Whenever you have a Carnot cycle, Va into Vc equals Vb into Vd. Okay, so I hope this question is clear, right? The only solving part was over here, right? This was the concept behind it, and the answer that you got was 4 unit. Okay, I'll give you a homework question and then hopefully we'll take a leave. Okay, so question 16 over here, it is your homework question. It is slightly moderate to difficult category question, so you can pause and take a screenshot. Okay, so that's all for today's lecture. I hope you enjoyed it. I'll see you soon in the next class. Don't forget to follow the word series which is going on my Instagram, which will help you boost your score in the English section of the paper. Also share this video with somebody, help them in their BITSAT preparation, and like this video, subscribe. Keep enjoying physics.